Okay, so today we're doing something that we haven't done before, and that is a thing called the sine rule. Oops, don't need that there. Let's get rid of that. Thing called the sine rule. So, unlike the SOHCAHTOA stuff, which works for right angle triangles, the sine rule can be used in any triangle. All right, so any triangle is the sine rule. Doesn't matter what the angles are. Now, having said that, we do need some certain information to work and use the sine rule. So it says here, so if your problem involves two sides and two angles, doesn't matter whether you know which ones you know, but as long as there's two sides and two angles involved in the question, you can use the sine rule. And of course, it's for triangles. Now, it's just poking down the bottom here. There's in your textbook there, and we're talking about the Cambridge textbook here. Page 393 has a proof or a derivation, whichever you prefer to use, of the sine rule. So if we have a triangle like this, so it's triangle ABC, capital letters for the vertices, and then we use little letters for the length. Now, side A is opposite to the angle A, or vertex A, angle A. Side B is opposite angle B, vertex B. And side C is opposite angle C, vertex C. So there's three ratios, and they're all equal to each other. So the side length A over sine A would be the same as side length B over sine B, which would be the same as side length C over sine C. Now, I said up at the top there we involve two sides and two angles. So depending on which sides and angles you are, you choose two of these three things to be equal to each other. All right, the note here, I've already gone through that. So lowercase denotes the side, uppercase denotes the angle at that vertex. And remember, it's sides and opposite angles. So side, opposite angle, side, opposite angle, side, opposite angle. All right. Of course, that would also be, when you get to year 12, it's on the formula sheet. Now, of course, what we can do is we can flip everything over, and you could also write it as sine A on A equals sine B on B, sine C on C. So you could also flip all of those and get it written in this form. And personally, when I'm finding a length of a side, I use this first version, and if I was trying to find an angle, I would use that version there. It just saves a bit of manipulation. You can certainly just use this for everything. All right, here we've got a triangle. It says in the triangle shown, it should be, in the triangle shown, right, in the triangle shown, find the length of AB. So we're trying to find this length here. Now this length is opposite vertex C, at opposite angle C, so that's why I've already put the little c here. So I'm going C over sine C. And then I've got this side here. Now when I have a look there, again, let's put that there. There we go. There we go. B here. All right, so I'm looking at then B over sine B. All right, so side length C over sine 31 equals side length B over sine 70 times both sides by sine 31. Get your calculator out and do your calculation, and you find to 2 decimal places that side length AB is 5.48 centimetres. Alright, all seems pretty straightforward. However, if you are given 2 sides and a non-included angle, so up here we were given 2 angles and a side and had to find the same side, but here if you are given 2 sides and a non-included angle, so again we get 2 sides and we've got an angle, there are 2 possible triangles. Alright, so in this particular case here, so say I've been told that length AB is 9. I've been told that angle ABC is 40, and I've been told A to C is 7. But as you can imagine, it doesn't tell me anything about this angle up here. So if I was to draw a circle, for example, which is like what I've done here with this, draw a circle of radius 7, you'll notice when you draw that circle of radius 7, it intersects this line here, B, that's going out. It will intersect that line in 2 places. Here, this one I've called C. This one I've called C. And then again here, this one I've called C dash. So there's 2 possible triangles that I could have. I could have this one there, or I could have that one there. So sometimes this one is referred to as the ambiguous case, because you're not sure, are we wanting that angle there, or are we wanting this bigger one here? So we're not sure about that. So what we need to do is we need to actually recognize that there's 2 possible answers in this case. All right, and it's reasonably not too difficult to figure out, because if I drop a line down here, down the middle, well, in fact, this is, because that 7 and that 7, that's an isosceles triangle, and so if I drop that down the middle there, actually I don't need to drop that down the middle, this angle here, they're the same, and so once we know that they're the same, we can quite easily figure out the angles opposite to this 9. All right, and I'll get to that, how we do that. All right, so here's an example. In a triangle XYZ, find angle Z given that Y is 25 degrees, length of Y is 5 centimeters, and the length of Z is 6. All right, so what I would do is I would draw like this. I'll go, whoa. And so I probably want to use a ruler, unlike myself. And so this I'm going to make Y down here. So that's going to be 25 degrees. All right. Now this side here is going to be my 6. So the Z's over here somewhere. Oh, sorry, that's Z. Little lowercase. Uppercase Z is over here somewhere. Okay, so yeah, that means that this is X up here. And the length of Y is 5 centimeters. So if I have a 5 centimeter, let me change the color on this one. if I have a 5 centimetre circle, you see that, a 5 centimetre circle, there it is, a beauty. I'm so talented at drawing, really. Don't know how I do it. So that means we've got two possibilities. We've got that down there, or we've got that up there. Now, because I'm such a great artist, you can see that this length here, 5, and this length here, we've got that isosceles triangle that I talked about. All right, so the 5 is the y, opposite angle y. 6 is here, and I'm after, which is z, and I'm after the angle z. So because I'm after the angle, I'll say sine z over length z is equal to sine y over length y. All right, so sine z over z, and z is 6, sorry. Look at opposite to the angle, 6 equals sine y, so the angle at y down there, 25, over length y, which is 5, times both sides by z, and not z, by z, which is 6 times sine 25 over 5. Then get our calculator out, of course, because our calculator, and of course to find the angle we need inverse sine of all of this stuff. So you can use on your class pad, you can use templates and all the rest of it to figure out that this particular angle is 30.47 degrees. All right, now, as I said before, there is two possibilities. And so there's this angle in here, or there's this angle in here. Now, 30.47 is clearly this, that one. So that's 30.47. Now, because of that, forget about this stuff over here, this triangle here is an isosceles triangle, then that means this here is also 30.47. So if I'm looking for that angle in there, that big one there, straight line, so my other angle, so the other possible is 180 minus 30.47. So with the ambiguous case, that's always going to form an isosceles triangle there. That angle and that angle are always going to be the same. So this one is always going to be 180 minus. And so when you do that on your calculator, you get 149.53 degrees. All right, so that's really the only tricky bit, is if it's an ambiguous case. And what I always would try and do is draw the diagram so my unknown length, and I shoot that out, keep that going long, is there. My known angle is here, and so I'm always drawing a diagram like that. All right, so if you want some more clarification on that, make sure you get some help, and as always, have fun.